Good morning all, my name is Michael Quilligan and I will be presenting today on the development and testing of a deployable double-layer Tensegrity grid. This was a joint project between the Universidad de Cantabria in Spain and the University of Limerick. The collaborators from Cantabria were Valen Gomez, Cristina Manchado and Cesar Otero. This is an outline of the presentation structure. After a brief background, I will describe the development of the grid, in particular the design of the connection nodes. This will be followed by a description of the grid assembly and testing procedures, and I will then provide a summary of the main results and some observations which have followed. Tensegrity is a structural principle based on the use of isolated or continuous pin-jointed components in compression inside a net of continuous tension, as illustrated by the Tensegrity prism here. Although the concept has been studied for many decades, relatively few examples of Tensegrity structures have been used for civil engineering purposes. One of the most iconic, however, is the Kurilpa Bridge in Brisbane, Australia, which exhibits certain Tensegrity structural principles. This paper describes the development and testing of a deployable double-layer Tensegrity grid. These types of structures can typically be easily stored, transported and erected within a short time frame, allowing for many uses such as temporary shelters, exhibition roof structures, etc. A potential advantage of Tensegrity structures is their kinematic indeterminacy. When arranged as a foldable system, only a small quantity of energy is needed to change their configuration because the shape changes with the equilibrium of the structure. As a result, these grids are potentially optimal structures to be incorporated into space applications or temporary shelter structures. Relatively few examples of this type of structure exist, with a couple of examples shown here from Bordaballa and SMIE, the latter being one of the more recent examples which made use of the V22 expander type elements. The grid constructed for this work is termed a Quastruct S1, which is shown here. This grid type is composed of modules of 4 struts with nets of cables resembling an S shape on the upper and lower layers. The Quastruct S1 is a Class 2 Tensegrity structure. The classification number here defines the number of struts meeting at the same joint. For this project, a 4 by 4 meter grid was designed, containing 16 equal 1 meter cubed modules. The grid was analysed using the TOI-GL graphical simulation program that implements the discrete element method in real time. It's a very good program which provides a versatile method for the design and static analysis of Tensegrity systems, and it permits direct feedback on structure behavior to real-time changes. Member elements were then designed in accordance with Eurocode 3, 27mm circular hollow sections and 4.75mm diameter galvanized high tensile steel wire rope were used throughout the structure. The total mass was 233 kilos, which is equivalent to approximately 14.5 kilograms per meter squared, and this is considered relatively light for a space frame structure. A schematic workflow illustrating the methodology adopted to complete the final development stage of the project over a relatively short period of 2 months is shown here. A key part of the work was the development of the connection nodes, with significant work going into their design and prototyping using a range of models prior to undertaking the full-scale testing of the structure. The design process of the nodes is further illustrated here, with samples of the hand sketches, 3D computer models, and full-scale prototypes shown. The design criteria for these nodes were numerous. The central node, for example, had to adequately transmit forces of up to 9 converging members, illustrated here, whilst facilitating folder of the structure. A compact design was important to minimize member eccentricities, and due to a very tight budget, standard off-the-shelf elements had to be used where possible to minimize cost and fabrication time. In terms of the assembly, a full-scale timber template was used to facilitate accurate placing of the nodes. A detailed fabrication sequence was developed, which included the pre-assembly of certain component groups to streamline the process. The broad sequence involved the placing of the lower cable net, followed by the strut sub-assemblies, and then the upper cable net. At this stage, the grid was stable, but it wasn't rigid. The diagonal cables are then placed and the grid completed by the addition of the vertical tensors and the closing of the inner node fixing plates. The vertical tensors seen here are the active elements of the structure. Through shortening of their length using a turnbuckle, the grid is forced to expand a bit like a scissors framework, and a state of self-stress is introduced into the grid. It was determined that a shortening of the tensors by 50 mil would achieve the targeted self-stress and provide a stable and rigid grid, which could then be lifted into position. In order to monitor the behavior of the grid under loading, 5 compression struts and 3 tension cables were instrumented. The struts were chosen so as to provide data on 2 heavily loaded, 2 moderately loaded, and 1 lightly loaded member. Each strut was instrumented with a pair of biaxial strain gauges set up in bridge format. The instrumented areas were then protected with a covering to avoid damage during the assembly and testing of the grid. A cable member was chosen then in each of the upper, lower and diagonal layers and were instrumented with 5 kilonewton load cells. Displacement of the grid was monitored using a Leica total station with reflective targets attached to each node on the upper layer. Measurements were then taken after each load increment. The grid was supported on 4 1.2 meter high fabricated steel posts, which allowed the load to be applied and sufficient space for structural testing. Due to the scale of the structure, load was applied in the form of small precast concrete slabs to 8 nodes on the lower grid. These nodes were selected to ensure an even distribution of load, whilst allowing for their safe application from outside the structure boundary. The slabs were attached to the structure via specially fabricated steel hangers, which you can see here. There were 6 increments of live load applied, beginning with the steel hangers alone and finishing with the hangers and 5 concrete slabs. The maximum total load applied, which is shown here in this photograph, was approximately 8.5 kilonewtons, which equates to approximately 0.5 kilonewtons per meter squared. This is comparable to the characteristic load value of 0.4 kilonewtons per meter squared, which is defined in Eurocode 1 for roofs with nominal access. The live load deflection curves for 6 sample upper layer nodes are shown here. It is evident that the structure behaves in a generally linear manner, with the mean maximum live load deflection of approximately 60 mil recorded. The experimental deflections, however, were significantly greater than those predicted by the analysis model. The TOI-GL model predicted a mean live load deflection of approximately 25 mil. Some reasons for the differences between the measured and predicted results are discussed in the following section. This figure here illustrates the compression forces in the instrumented struts under loading. The response to load is generally linear, with a maximum force of approximately 3.3 kilonewtons recorded in strut 25. The ratios of theoretical to experimental compression forces for three struts are shown here for each increment of live load. While there is broad agreement of the forces under self-weight, it is evident that the theoretical and experimental values diverge in a linear manner as load increases, with the experimentally recorded values less than those predicted by the analysis model. Here, the figure illustrates the tension forces in the instrumented cables under loading. The response for cables 93, which was on the lower layer, and 278 on the diagonal layer, are generally linear in response to load. However, cable 163, which is on the upper layer, clearly goes slack upon loading. A maximum force of approximately 1.2 kilonewtons is recorded in cable 93. The ratios of theoretical to experimental tension forces for cables 93 and 278 are shown here for each increment of live load. Again, the theoretical model significantly overestimates the tension forces in the cables, particularly under self-weight. During testing of the grid, a number of observations were made regarding the performance of certain details. First off, it was noted that the top of the steel supports, shown here, rotated inwards under loading. Rotation of a number of outer nodes was also observed due to the high level of eccentricity between converging members, in some cases up to 80 mil. These rotations resulted in the slacking of several of the upper cables, reducing the grid's stiffness and increasing its deflection. Improvements to the support arrangement and node design are suggested for future works. The addition of the inner node fixing plate, which is shown here, reduced the tendency of the node to rotate under imbalanced loading. Whilst this was a positive initially, it is possible that its behavior is then closer to a fixed node than a through pin. This could introduce bending moments in the members, with a resultant change in the distribution of forces within the structure, and is an area that requires further investigation of the team. The method of applying self-stress to the structure is a very important area which can have a significant impact on the member forces. In this work, the vertical tensors are shortened to introduce self-stress. However, there was no direct control on the tension in the remaining cables. If the initial tension level in those cables is not set correctly, the tensions induced by the self-stressing could be imbalanced, affecting the overall stiffness of the structure and the distribution of forces within it. In contrast to these details, the TOI-GL analysis model considers perfect pin-jointed nodes with no eccentricity, no rotation, no bending moments, no friction. And as such, differences between the measured and the theoretical values are not unexpected. This paper has described the development and testing of a novel deployable double-layer tensegrity grid. A large-scale 4x4 meter grid was designed using the Qua-Struts S1 tensegrity module, with nodes developed to cater for the connection of multi-directional cables and struts, while allowing for member rotations to permit folding of the structure. The grid was constructed, instrumented, and load tested to determine its functionality and structural performance. The overall behavior of the grid proved satisfactory, and the structure folded into a compact cluster of approximately 0.56 meters in diameter, which is shown here. While the overall behavior was as expected, recorded deflections were greater and measured member forces were less than those predicted by the analysis model. Potential reasons for these differences have been discussed. It is concluded that the developed grid offers many advantages, as it can be easily stored, transported, and erected within a short time frame, and therefore has the potential for many uses. However, further work is required to improve the modeling of the structure, to better predict the structural performance, as well as improving the node design and the methods of applying self-stress. Thank you very much for your attention today. If you have any questions, I will be happy to answer them during the Q&A session which follows.